Late at night on the second to last day of the 2009 Copenhagen Climate Conference, leaders from the world's most powerful nations gathered in a cramped, windowless backroom. They had flown into the city expecting to attend a lavish state dinner and sign a prearranged global climate treaty. Instead, they found gridlock. The formal negotiating process had dissolved entirely into protests and bickering. By the time the international conference ended without a binding deal, green activists were labeling the summit a crime scene. But the talks didn't break down because of political sabotage. They broke down because the proposed treaty forced the developing world to choose between protecting the environment and lifting their citizens out of poverty. Look at this distribution of the global population. Roughly 1 billion people live in wealthy nations, and their leaders arrived in Copenhagen focused heavily on capping emissions. But another 6 billion people live in developing countries, and their absolute priority is escaping poverty. When we shift this chart to show energy consumption per capita, the math becomes clear. Improving basic human living standards requires a massive, unavoidable spike in energy use. South Africa, for example, has worked to connect roughly 20 million citizens to the grid since the end of apartheid. To meet that massive new energy demand, they had to build enormous coal plants, like the 4,800-megawatt Medupi generator. Asking developing nations to simply conserve resources and consume less ignores physical reality. Almost 1.5 billion people are currently living without electricity. They are going to turn the lights on, and they will use absolutely whatever fuel is available to do it. To understand exactly how global emissions are calculated, we can look at the mathematical framework used by the Intergovernmental Panel on Climate Change. It's called the Kaya identity. This equation dictates that total emissions are the product of 4 specific variables: global population, economic consumption per person, energy efficiency, and the emissions produced per unit of energy. If we treat these variables like mechanical levers, we can test our options. The first lever is population. The global population is set to grow to over 9 billion by mid-century. We cannot pull this lever down. The second lever is economic consumption. Pulling this down means intentionally stalling economic growth in developing nations, keeping billions in poverty. That is the exact condition the developing world rejected in Copenhagen. The third lever is energy efficiency. We can make our machines and grids better, and we are. But those incremental gains cannot mathematically outpace the compounding growth of a rising population and an expanding global economy. That leaves exactly one variable left to solve the equation: to reduce the emissions produced by the energy we generate. To pull this final lever, we need a massive transition to zero-emission power sources. Engineer Saul Griffith calculated what it would take to build that infrastructure using current green technology over the next 25 years. He mapped out a theoretical continent he called Renewistan. To cover the globe without fossil fuels today, you would need to install 100 square meters of solar cells every second. You would need to erect 12 wind turbines every single hour. And you would need to build 3 1,000-megawatt nuclear plants every week, continuously for 25 years. The sheer physical footprint, the mineral requirements, and the construction scale mean by current renewable technologies and organic practices cannot solve the equation alone. Hitting these hard physical limits makes the climate crisis look like an inescapable trap. But we have been here before. In 1798, Thomas Malthus predicted that human population would outgrow the available farmland, leading to mass starvation. In the 1970s, Paul Ehrlich modeled similar doom, forecasting that humanity would run out of critical raw materials. Their predictions failed for the exact same reason. They assumed human capability was static. They modeled future constraints based entirely on the tools of their present, missing our capacity for invention. Malthus's starvation trap was shattered by people like Fritz Haber. In the early 20th century, Haber figured out how to use steam and methane to pull nitrogen fertilizer directly from the atmosphere, vastly multiplying the amount of food the Earth could produce. Humanity has survived every major resource crisis, not by managing our own decline, but by inventing technologies that stretch the boundaries of what the planet can support. That same logic applies to the climate crisis. Solving it means letting go of romanticized ideas about returning to a simpler, supposedly natural state. Blocking high-yield genetically modified crops or zero-emission nuclear power out of ideological purity restricts the exact tools we need to feed and power the planet without choking it. We cannot conserve our way out of this problem, while billions of people still need the basic infrastructure required to live healthy lives. The developing world will continue to grow. We don't have to choose between human progress and a stable climate. We just have to push technological innovation harder than ever before.